Thank you, everybody, for joining. This is the fourth webinar in our aerospace or human factors in aerospace webinar series for the HFES Aerospace Technical Group. And just as a reminder to everybody, the webinars last about 30 minutes for a presentation and then about 20 minutes for questions after that. I'll start out with a few questions and then turn it over to the audience for questions. Today, our guest is Dr. Chris Wickens from the Colorado State University. He'll be talking to us about see-through displays. I'll let him introduce himself and start the presentation.
Okay, thank you very much, Rodrigo. It's really nice to talk to you all. I'm sure look forward to seeing a lot of you in person next October in Chicago as well. So I'm going to talk about see-through displays, HUDs, and HMDs, and the subtitle is When AR Meets AI, and we'll unpack that statement at the very end. So the inspiration for my, I would say, 40-year history or 30-year history of working on see-through displays was this little technical manual that NASA released called Cognitive Issues in Head-Up Displays. It came out in 1980 by Fisher, Haynes, and Price. I read it. I was just starting to work with NASA support at that time, and I really got intrigued by the findings in this particular study. So I'm going to use those findings to introduce really three phases of my research in the last, it's 45 years. In phase one, from 1980 to 2000, focused on attentional tunneling and the HUD. As I say, this little technical report reported of a 727 flight simulator study, and the authors found that flying with the HUD disrupted detection of the unexpected runway incursion more than did flying with a head-down display. A difference of 4.87 seconds versus 1.7 seconds. That's a 3-second difference, and on approach, that can be critical in terms of how rapidly you detect the hazard on the runway. Shortly thereafter, Alaska Airlines was the first airline to adopt the HUD as for standard flying procedures. And in the 1990s, along with Sandy Hart, developer of TLX, which you're all familiar, and Dave Foyle at NASA Ames, they supported me with 15 years of collaborative research, comparing the HUD versus the head-down display. In particular, when we could find studies that used equivalent symbology in both the HUD on the left and the HUD head-down display on the right. And I'm going to jump ahead to the next slide. There's another example of a comparison on the right. So we looked at performance with the HUD versus a head-down display across two generic tasks. One was standard flight path tracking, and the other was event detection, where we looked at the pilot's ability to detect events as either alerts on the display or off-nominal hazards beyond the cockpit, such as the runway incursion studied originally by Fisher, Haynes, and Price. What we then did was synthesize the results of all these studies we could find, and there were about 20 or so that existed by the time we tried to integrate the findings. We summarized it in a meta-analysis with Steve Fadden and Trish Fervers, again, comparing head-up displays with head-down displays. And the results of the meta-analysis were summarized by Z-score effect size measures. I think most of you are probably familiar with the Z-score, or the D is a measure of how big is an effect statistically. And what the collective wisdom of all of these studies revealed is that overall there was a benefit to the HUD over the head-down display. For tracking, this benefit was very large, a Z of 5.9. For the detection of discrete events, it was smaller, but still highly significant, Z equals 3.375. So there's a general benefit to using the HUD over the head down display, but there are a couple of exceptions. During cruise flight, we only looked at tracking of airspeed and heading. The problem with time.
Seems like we have some echo.
audio.
Okay, there we go.
There was actually a small HUD cost, and that was basically if you're looking through the HUD at a bright outside scene, you're going to have lower costs in processing the display, particularly for altitude and tracking heading information. But more importantly, during the landing phase only, there was a cost of the HUD for detection of events, particularly detection of low salience, far domain, unexpected events, such as a runway incursion or maybe some construction equipment that are left on the runway. You can see the runway incursion down there in our little graphical image in the lower right. So what we did then basically was to replicate the original Fisher, Haynes, and Price study, but now we had some strong statistics to back it up. Another finding that came out of the meta-analysis I did with Fadden and Ververs was the overall advantage of HUDs, which we saw up here on the top, actually grew when the HUDs used conformal imagery, that is, imagery on the display that was conformal or aligned with its counterpart in the far domain, such as the horizon line in a HUD or a runway overlay. And what the conformal imagery did was to create what is called scene linking between the near and the far domain. This is a concept developed by Dave Foyle. And basically, when the image on the HUD moves in synchrony with the view to the outside, it essentially joins those two as a single image and facilitates the divided attention between the two domains. Also, we found that when you use this conformal imagery, it minimizes the amount of clutter on the display that might disrupt the detection of events in the far domain. So that's the end of phase one of our research, my research with my colleagues, on looking at this issue of HUD prevention of off-nominal events. From 2000 to 2010, I started another series of studies, again with NASA Ames, but also with NASA Langley, where we looked at HUDs and the detection in general of any kind of off-nominal event. That is, unusual, unexpected events that any given pilot may never experience, but collectively across pilots, some do, such as a runway incursion. We joined the NASA Ames research with research on NASA Langley's synthetic vision systems, the SVS, or the 3D highway in the sky, or HITS display. This is work sponsored by Lance Prinzel at NASA Langley. Here are examples of the highway in the sky display. You can see here, and of course in the previous slide as well. And what we example is the pilot ONE, off-nominal event detection, with both the head-up display and the head-down display guidance, when that guidance was either presented in conventional ILS instruments or in a highway in the sky or tunnel in the sky leading to the runway. So essentially, our experiments compared either a control ILS display plus some sort of visual situation display with a highway in the sky display, which is conformal. And we could present these either here or here in either a head up or a head down display location. So it's kind of like this 2x2 experimental design in which we looked at a large number of experiments that had compared some or all of these four quadrants. In a concept I'll be coming back to, the important point is that when you have a head-up display here, you're going to have some clutter. You're going to have stuff on the display that's overlying stuff in the far domain scene, and that's a cost. But of course, when you have a head-down display, two separated displays, now you have to scan back and forth between them. So we talk about this as being the clutter scan trade-off that we've examined in several aspects of our research. Our real question, experimental question in this phase of research is there attentional tunneling with the HUD? And also, does the highway in the sky display create some form of attentional tunneling? And will this attentional tunneling be reflected in the detection of unexpected events? And in basic psychology, the detection of unexpected events is often represented by the concept of change blindness. I'm sure many of you are familiar with the famous Simmons study looking at the detection of a gorilla walking across a scene. So we're looking for evidence of this change blindness or failure to detect unexpected events, either as a function of moving up from a head down to a head up display, which we had found previously, or as a function from moving from control instrumentation to a highway in the sky conformal imagery. So once again, we begin to aggregate a lot of the literature that we could find, looking at comparison, particularly of conventional instruments with flying with the HITs, to determine if there was an increase in an increase in miss rate when people were flying with the more realistic head up, head down display. The more realistic highway in the sky display, such as we see here. The results of this meta-analysis, and again, it was also based on a number of studies that we had done at University of Illinois, but also a number of studies done elsewhere, is when pilots were flying with a head-down display that was highly realistic, the highway in the sky, and there was an unexpected event in the outside world. Here we're showing a blimp that might not have been on the information conveyed by the ground to fly, to generate the display. Nowadays, this would be a drone out there that is unknown by air traffic control and undetected by the aircraft's instruments. And what we found is that the miss rate was 55% when people were flying with a realistic highway in the sky display, or the tunnel in the sky, and only 33% without. And across studies, this represented a significant cost to detection of unexpected events in the outside world beyond the aircraft when you're flying head down with a realistic hits rather than more conventional instruments. Let's see. So there seemed to be a pattern emerging. That is, the more realistic or compelling display, the hits, diverts more attention into the cockpit, reduces out the window scanning, and we've got some scanning statistics on that, and therefore it leaves the pilot vulnerable to out the world unexpected event detection failures. Well, following this, we developed a computational model of cockpit visual scanning or cockpit change blindness. This is called the NCEIV model. I worked on this with my colleague Jason McCarley and Kelly Steelman Allen in order to predict this form of change blindness imposed by more realistic head-down displays. Eventually, this led to an FAA-sponsored review of so-called display compellingness research. This was done with Michelle Ye at the FAA, where we asked, what are the features of a compelling display, such as high display realism, an egocentric frame of reference, a 3D display looks more realistic than a 2D display, and a colored display tends to have more features of realism than a monochrome display. In our review of other literature, not a meta-analysis, but just a review, examined all of these features of display compellingness in the cockpit and the extent to which they might contribute to some form of attentional tunneling. I should say what Michelle was concerned with, or the FAA, was when a pilot begins to use, say, a tablet, highly realistic tablet displays for aircraft guidance that are not part of the aircraft, but will that suck the attention away from viewing the outside world? So this leads me to phase 3 of my story, or my interest in see-through displays, where we moved from the HUD to the head-mounted display, both in aviation and on the ground. And this has been probably the last 8 years or so I've been interested in this. Both military fighter pilots, and for rotorcraft operations, we see examples of a HMD prototype. This is one for the Air Force, where you've got a HMD, and what it allows for, of course, is off-axis viewing of flight instruments. So I could be looking over here, maybe looking for contacts, and still see the instrument panel as I'm looking off the axis, where it's not possible when you've got a HUD. You've got to be looking straight forward at the HUD of the instrument, and so you can't scan to the left and right. Once again, now our research moved to the military, particularly the Marine Corps in battlefield operations, where we're comparing the soldier looking through an HMD to the scene beyond versus a soldier that now has to look at a tablet, for example, and then scan to the scene beyond. So again, this is the scan clutter trade-off. You've got clutter here, you've got scanning here. Well, a little bit of terminology is in order. In the HUD, we talked about conformal imagery versus non-conformal imagery. The conformal imagery is that which aligns with the counterpart, the horizon line, the runway overlay in the outside world. For the HMD, that similar contrast is between what we call world reference information, presented in augmented reality, or screen referenced information that is not in augmented reality. I'm sorry, that should be deleted. So an example of conformal or world referenced information in the HMD might be an overlay, the blue overlay of a particular mountain. And that overlay will always overlay the mountain no matter which way the head is oriented, because it moves in the opposite direction of head orientation to keep it superimposed. On the other hand, non-conformal imagery may be a digital readout of heading or a little mini map that always stays in the same location on the display, that is in screen reference coordinator, independent of head orientation. Okay, the use case of information on the HMD that we were particularly interested in is that which supports unexpected event detection, and in particular using the HMD to present a cuing to guide the user towards hazards out in the far domain. This is not us, this is the Air Force, but they're looking at a cue, a red arrow that may point to a possible enemy target in the airspace ahead. In our case, we looked at either a mini map or a augmented reality arrow to aid the soldier in searching for a target, for example, an IED somewhere in the forward view. It's hard to see here, but if we look at cued conditions, you can now have an augmented arrow that points to that target, the little green box, or for a non-screen or a screen referenced cue, you could have a little reticle circling where that hazard is on the environment as viewed from a top-down map. Okay, quick departure from the findings of this research. I want to talk about the potential value of the augmented reality target cueing for the Black Hawk pilot regarding the tragedy that happened a few months ago over Washington, D.C. And as I'm sure you all know, the nature of that tragedy, you had a helicopter southbound, you had a regional jet that was making an approach to runway 33 at the national airport. And what happened? This regional jet crossed in front of the flight path of the helicopter, who was flying low, and there was the mid-air collision. And now we can ask several questions, and I'm only going to talk about two of them here. And I think most of you are probably familiar about both the questions and the answers. What procedures put them on a conflict path? Was there a breakdown in air traffic control? And we know there was a partial breakdown simply because of the lack of adequate staffing. But the controller gave the pilots a cleared for visual approach, which required the pilot needed to assure air traffic control that they had the contact in sight. The helicopter pilot did indeed assure ATC they had the contact in sight, told the ATC so, and the ATC said pass behind, following the rules of the road. But the problem with this situation was communications ambiguity. There was a second aircraft out there besides the regional jet shown here, and the helicopter pilot was probably referring to this aircraft, not this aircraft, when they said contact in sight. And we assume they therefore did not notice the regional jet when they said that. Well, if we go to the forward view that the pilot might have had from the helicopter, what they would have seen is the non-hazard aircraft essentially drifting off their field of view from left to right, if you follow this collision geometry. And a moving target is salient because movement defines salience. That would have captured their attention, the motion capture, and they would have assumed that's the target that they had in sight. Whereas the hazard regional jet, because it is on a collision path, would have a steady bearing, decreasing range. This is the defining feature of a collision course. And the only change that the helo pilot would have seen is a gradual expansion of size or an increase of brightness of the lights, not salient, and therefore an invitation for a failure to notice or change blindness, particularly when you have another contact in the forward field of view that is more salient. But now we can ask the question, if that pilot wearing a head-mounted display, and they were looking through night vision glasses, had some sort of hazard cue that would have used some AI to infer that this is a collision target and put a red reticle around it or an arrow pointing it to it, presumably that would have prevented the collision. But let's return to the ground, to the domain of the Marine Corps soldier, and talk a little bit about the research that I've been doing with Emilio Warden on her dissertation, in which, amongst several things, we would compare the benefits of two types of target cueing to search time and accuracy. One would be the augmented reality arrow shown down here. The other would be the non-AR or screen referenced display that put a reticle around the targets. We found that both types of cues considerably helped the soldier to find the targets, an IED. For the arrow, average of 8.8 seconds, 92% accuracy. For the mini-map, which is screen referenced, 11 seconds, 84% accuracy. So we found a benefit to augmented reality cueing to both the speed and accuracy of hazard detection. And for the soldier in the field, this savings of about 2 seconds and the increase in accuracy of 8% can certainly make a tremendous difference if you're trying to look for hazardous material and hazardous objects or individuals as you're moving through terrain. But, and now we really come to the final message of the talk. Suppose that the cue is wrong. That is, suppose this arrow is not pointing to the hazard, but pointing to something over here that looks like the hazard. Well, the cueing in any sort of system, whether it's augmented reality HMDs, regular HMDs, or for that matter, HUDs, is going to be based on some sort of AI machine vision that is required to categorize an element in real time as being hazardous or not. But what we know from a wide variety of other research, and I spoke about this research to the Boeing company and actually to NASA in a webinar a couple of months ago, is that AI is imperfectly reliable. It makes mistakes. We all know that ChatGPT makes mistakes, but the example is from the TCAS system, where we have TCAS warnings coming on from elements about elements in the air that the pilot does not judge to be a hazard for various reasons. So AI is imperfectly reliable. It makes mistakes. It can miss a hostile or hazardous target, or sometimes it can cue a hostile, a non-hostile element, which would be considered a false alarm. Well, the findings of the research I did with Amelia Warden is the benefits of more realistic cueing, that is AR cueing, when the artificial intelligence is correct. That's the benefits I showed you on the previous slide. But there were greater costs of the more realistic cueing when the automation made an error. In other literature, this is called the automation bias. It involves following the guidance of imperfect automation down the garden path, trusting the automation when it couldn't be trusting, and trusting it more when the guidance provided by the automation is in a more realistic form. This is just a sample of the data that came from Amelia's work. We looked at the errors in users in detecting targets when their cueing of the targets was either in an augmented reality arrow, such as this, or in a less realistic mini-map, such as the reticle surrounding the target on a map in the real world. And we found that when the automation was correct, you had no errors with the gaze, the arrow, augmented reality arrow. You had some errors with the mini-map. But, and this is the key, when the automation made a mistake, you had a significantly higher error rate when the automation was the highly realistic arrow than when it was the less realistic mini-map. So this is a sample of data that leads to, and now I'm going to draw back and talk about the more general conclusions of all of the research with both HUDs and HMDs. The first conclusion is that the see-through display, either the HUD or the HMD, is generally helpful. In fact, quite helpful in the case of the HMD, in spite of the cluttering the view of the outside world beyond created by an overlapping imagery. The reduction in scanning when you don't have to look head up and head down clearly wins this scan clutter trade-off. And we have statistics to say how big is the margin of victory. But both HUDs and HMDs can hinder the detection of unexpected low salience hazards in the scene beyond. And those hazards can present major sacrifices or mitigations of safety. The high realism of 3D displays can be a source of attentional tunneling in the head down displays, whether it's head down or head up, and in particular head down, because a highly realistic display will actually be compelling and guide more scanning to it, sacrificing looking up at the outside world. And lastly, when the 3D realism of augmented or AR displays is brought into the HMD, this may too be a source of attentional tunneling if the AI or the artificial intelligence or the automation driving the display is wrong, creating a miss or a false alarm. And so these are the circumstances when augmented reality in the HMD meets artificial intelligence, or when AR meets AI. So that ends the presentation I'd like to make. I want to thank you for your attention. I want to acknowledge students, several students that have been involved in this research, particularly Trish Ververs and Steve Fadden, and from the aviation side, Amelia Warden from the HMD side. I would certainly want to acknowledge the sponsors we had from NASA Ames, particularly Dave Foyle, NASA Langley, Lance Prinzel, and also from the Office of Naval Research for our work on HMDs in the military, Peter Squire, our sponsor. And much of this research was carried out on the aviation side, all of it, in fact, at the University of the Illinois Institute for Aviation. And for this, I give great credit to the late Hank Taylor. He's passed away since I worked for him, but was a real source of inspiration in much of this research. So these are my two emails. If you want to email me about getting more articles on this, I'm happy to send them forward. And I will work to try to get this particular presentation sent to Rodrigo. The problem is it's a greater file size than can leave my lowly little Apple. So I've got to break it down into a couple of subfiles, but I'll do that later today if you want access to that. But I also believe this presentation was recorded. Is that correct?
That is correct. And the recording will get posted in the next few days for everybody to access.
And that will include the power of the view of the PowerPoints. So
yes.
Okay, well, that's the end of my presentation. We've got time for some questions or comments or thoughts.
Great. Thank you so much, Dr. Wickens, for the presentation. I'll ask a question at first, and then I will turn it over to the audience to ask their questions. My question has to do with this last point that you were discussing about when the automation is wrong or can mislead the human. And I wanted to ask, do you think that will be a limiting factor in implementing these technologies in practice? And if so, what's the path forward to address that? Is it only improving the quality of the AI algorithms, or are there other mitigations that we can put in place to help address that problem?
Real good point. No, it's not going to limit the development of applications, I'm pretty sure. And certainly the Air Force, Navy, and the FAA down at CAMI are looking very seriously at the HMD applications. My feeling is simply that evaluations, whether in flight tests or simulator tests, have to examine the potential. They have to put off normal events in and find out if there is a sacrifice of safety. There are a number of different solutions that we're working on at Colorado State that can mitigate these problems, such as changing the transparency of the image intensity. So they're human factor solutions related to decluttering the display. But certainly there are really important training implications for pilots or any users that are using these techniques of knowing when and where the vulnerabilities will occur, perhaps training strategies, scanning strategies that can mitigate them. So as with any human factors endeavor, it's a multi-pronged approach. And I think the pronged approach is to tweaking design parameters, the visual parameters of the HMD, but also the training of the HMD user.
Great. Thank you so much. I want to open it up for other people to ask questions as well. So if anybody has a question, you can either unmute and ask your question or post your question in the chat and I'll read it out, whatever you feel most comfortable.
Can you hear me?
Yes.
Yeah, hi, Dr. Wickens. Very great presentation. I've flown a lot of night vision gala work. I've flown a lot of
Yes, Lauren.
infrared, work.
I've cited your work on our early paper. So cited it in a good way. Yeah.
I was excited to see your analysis of the Black Hawk in the DC area. That was very informative to me and a reminder of several things that I hadn't thought about. And so I appreciated that. That, in addition to the information that you provided in all these cases, I hope to be able to look at your webinar later and just pick apart all those different things that you're instructing as you go along. And I think all of those are very, very valid. I can remember when conformal symbology for HUDs and HMDs and other things came along, and what a value that was. But I also see the other detractors that that you mentioned in your video. So really, really appreciated this instruction. Thank you very much.
Well, thank you. And I appreciate your comments too, because a paper that I wrote with Trish Ferrers relied pretty heavily on your work on HMDs. And I'll send that along to you if you send me an email, message. I think we've got it digitized. So
sure, be happy to. Thank you.
Any other audience questions?
Hi, Dr. Wickens. This is David Newton from the FAA CAMI. First of all, I really appreciate your presentation. This was stuff that we're looking into, and it's very interesting. I look forward to reading any publications you have out of this. I just completed a study comparing monocular to binocular HMDs and found with a runway incursion, there was no difference in the very first unexpected incursion in terms of the delay in detecting. However, as pilots experienced subsequent incursions and then became or anticipated, they were quicker at detecting incursions with the monocular HMD than with the binocular. So I'm curious, looking at it through the lens of your analyses, display compellingness, and so forth. Do you see any? Are you looking into the monocular component of these HMDs?
No, we have not. And one of the reasons is, of course, the research that we're now doing for ONR is basically funded by the Marine Corps, the ONR, and they really want us to use the system, the HMD system that they're putting in place, which is binocular. So in terms of kind of our research for that particular customer, we're using the binocular. And of course, the other thing is the binocular is best suited for providing some sort of conformal displays in the sense that you now have depth or binocular disparity to convey depth perception. But the issue of binocular and monocular is, I think, extremely important. I did some research with Michelle Ye of the FAA way back 20 years ago for the Army, where we looked at some comparisons, at least what the literature had shown. And while I've got you on the line, David, you presented at Aspire last year, right?
Yes, I did.
That was the work with Dennis Behringer?
That was Dennis helped with that, yes. So yeah, that's where we found some workload and performance differences between monocular and binocular.
So let me interrupt. I've been trying to, but because of some sort of corruption in the, I have not been able to get hold of your paper that you presented.
Oh,
would you do me the kind favor of sending that paper to me as an attachment? And
absolutely.
Any subsequent write-ups that I have. Yeah,
I will certainly do that. I'll send you the full CAMI reports we were developing on that.
Okay, and a quick diversion I can say for FAA CAMI, go Oklahoma City Thunder, but a real diversion. So let's go back to questions. But
thank you.
Yeah, and I'll start a little dialogue of communications with you as well on this issue, because I'm extremely interested in the work that you guys are doing.
Wonderful. Looking forward to it.
Dr. Wickens, if I could ask another question.
Yeah.
I am curious about conformal displays and HMDs and working with conformal displays off axis. Do you have anything to remark on that?
No, other than we're starting a research track here at CSU, trying to work with the Air Force and the Navy at the Air Force research labs, if they can find money, to look specifically at that issue. Yeah, yeah.
That's good to hear. From experience, especially with one of the HMDs that I worked with, I almost came to the conclusion, unless you did a good job, you shouldn't take some of that conformal, those displays. A non-spatial, okay, offsite or off axis, but always worried about the conformal part of it. And, that also gets into the head tracker and things of that nature too.
Yeah.
Thank you.
That's the issue that Hank Williams at the research labs in Wright-Patterson is very interested in doing as well. Some of the Air Force slides I showed is from their work. Yeah. So, gotcha. And that issue is certainly not been solved. Yeah.
And I think the other part too, as far as the night vision information, there is no putting I don't know what you call Pandora back in the box or anything of that nature. Mm-hmm. It's going to continue in the future to be able to work at night. I've worked with some of the FAA people when they're first starting to use night vision goggles, and what was interesting is the fact that was considered an appliance and not attached or aircraft equipment in terms of the certification business too, which also added some confusion on how to do that. Do you see a lot of night vision goggle with symbolic displays now, or at least the head tracked displays on night vision goggles?
And again, we haven't looked at that specifically with the NVGs in our research. Yeah. So we're looking, we're kind of trying to solve the day vision problems, which so much of it relates to clutter. But that's another avenue to take it. I'd love to take it in this direction as a career. My career is so close to retirement at this point that I'm not sure I can. I'm hoping to pass that on some of my colleagues.
I've retired many times. I think you could too.
Yep, exactly.
The one last thing, infrared especially, and I've seen fusion, I've seen infrared, and I've seen image intensifiers. The one thing that really, I guess, bugs me a bit, and I'm going to talk about the sensor itself, because it's all delta T's. There's a lot of times that images are not complete.
Yep.
In other words, you're not looking at a TV screen, for example, and that has always been a concern to me, and how you make up for that in certain environments where there aren't good delta T's, and how you do that with symbologies and things of that nature, if that's even possible.
Yep.
Anyway, thank you.
Okay. Just as a quick, again, another side thing, I'm noticing on my screen, I've got this mass array of names, and it's incredibly helpful to have the cue, in this case, a green reticle surrounding the person talking. So,
interesting.
Thank you. Cued guiding visual scopes makes my task easier.
Yes. Thank
Okay.
you, sir.
I see we have a raised hand, so you can ask your question.
Thank you. Hello, Dr. Wickens. This is Shirtao from University of Waterloo. Me and my students, we're right now exploring AR head-mount displays for general aviation student pilot training. So we found that most of the previous work are done by either for commercial airlines or for military pilot. So do you think with a lower budget and some low-cost devices like HoloLens, but Microsoft discontinued that, is there a future for general aviation applications of AR like HMD?
Oh, definitely. Yeah.
And
that's going to be a more rapid progression, probably certainly than in commercial aircraft, given the challenges for certification in the commercial aircraft, greater challenges. Yeah.
Mm-hmm. And for those low-cost devices, usually the field of view is smaller, and the reliability is lower. We talk to some pilots and instructors. They always have the fear that, oh, what if, while they're wearing those during training, if it stops working, right? They're still on their head. They have to remove this from their head. So sometimes they prefer, can I use maybe iPad, those tablets you can put it on the screen? Sure, then they're not head mounted anymore, but still provide some information. Like they do want to compare the pro and cons of those different versions of displaying the information.
Yeah. I agree. I mean, those comments make sense. I would very much appreciate it if you have any published work or conference papers or anything like that, if you'd send them my way. I'm trying to, as I like to do, since I don't have a lab here, I'm working with somebody that does, but they're not an aviation expert, but I like to collect information.
Thank you. One PhD is finishing his work, and he did a tool study using HoloLens version 2. We're looking for a new device, like since HoloLens has stopped being produced. Are you aware of any those like devices we may use in the future?
No, but I can put you in touch with Amelia Warden, my PhD. She has all the technical know-how on the strengths and weaknesses of different HMD platforms for this kind of research. Yeah.
Okay, excellent. Thank you very much.
But so please, you've got my email address. Send me on the, any published work that you have in this.
Yes, will do.
Thanks.
I'll ask one final question. I know we've only got 10 minutes left and you have to jump off soon, Dr. Wickens, but I'd like to ask for the students that are in the group or the younger members of our technical group who are just kind of getting into this field, what resources do you recommend looking at for understanding this kind of work or getting into this field of work? You mentioned a lot of your own papers in the slides, but besides those, are there other resources you recommend?
You mean resources in terms of infrastructure to support research?
Yeah, or papers that people might look to learn more about this subject, or classes, anything that could help somebody who wants to get into this field get into the field.
Yeah, well, I'm certainly happy to provide some of the papers that Amelia and I have written on this area. It doesn't seem to be an area that's coupled with a lot of good empirical research, with a adequate sample size to draw statistics, make statistic generalizations. So yeah, I mean, again, contact me. I can send you some papers.
Sure.
Definitely contact Amelia, and she's now an assistant professor at University of Michigan IE department, working. So, and she's building up a lab and building up a collection of sources, papers, and so forth. Yeah.
Sounds good. I'll reach out and then send that out to the group later on.
Yeah.
Well, thank you so much for taking the time to talk to us today. This was a great webinar. Thank you for being flexible as well, being able to postpone it a week due to our difficulties last week. I'd also like to say for the rest of the audience here, we're always looking for other guests to come on to the webinars in the next few months. So if any of you are doing interesting work that you think the rest of this group could benefit from learning about, please reach out to me, and we'll find some time to put you on a webinar as well. But thanks again, Dr. Wickens, and we'll stay in touch.
Okay, and I see again through my list of names a number of other people I know, Colleen Donovan and Sean Dougherty up there and so forth. So hi to all of you, and I look forward to seeing you guys, many of you at Aspire, they now call it. I still want to say HFES, but I'm going to be correct and say Aspire in Chicago. So, and thanks again, Rodrigo, for the invitation and the opportunity to talk to you guys. All right.